Okay, two more vocabulary words for this section. We say that a point P naught is a source if the divergence of our vector field F at P naught is positive. And we say that a point is a sink if the divergence at that point is negative. Okay? And I want to just explain that in the context of fluid flow. Okay? So if I have a point P naught, and I'm just going to draw a very small sphere around P naught. And if we suppose that the divergence of F is continuous, and we're generally working with vector fields that are continuous and have continuous first partials, so that would make the divergence continuous. So if the divergence of F at P naught is positive, then if everything is continuous, it's going to be positive in a very small region around P naught. Okay? So I'm going to make sure that I draw this disk small enough that the divergence of F is positive over that entire region. Then I know that I can calculate the flux across this boundary surface. So if I call the boundary surface S, I can calculate the flux as F dotted with N ds. But I also know that I can calculate it as the triple integral of E, where I'll let E be the enclosed solid, of the divergence of F dV. And if the divergence is positive, that means that the flux is going to be positive. So what that would mean is that there is more stuff flowing out than flowing in. If I had the same amount of stuff flow into the region as flow out of the region, the net flux would be zero. But if the flux is positive, that's saying that more stuff would be flowing out than would be flowing in. But in the context of fluid flow, most fluids are what we call incompressible. So a certain volume of that fluid is going to contain a certain amount of that fluid, and that's going to have a density function, so it's going to be a certain amount of mass. I can't suddenly have more stuff inside. And yet, if I've got more stuff flowing out than I have coming in, then suddenly I'm going to have less mass on the inside than I did previously. The only way that's possible is if we say that this is somehow a source. So somehow there's liquid on the inside that got there some way other than flowing in. That sounds kind of weird. But let's suppose that I had a gas particle that passed through here and then condensed and it became liquid. The flux was only keeping track of liquid coming in and going through the surface. So if liquid enters or leaves as a gas and then condenses or evaporates, suddenly that can change the amount of liquid that I have on the inside. And so a source would be a place where we would have essentially condensation occurring. So somehow we entered that region as a gas and then poof, we condensed and now we have more liquid than we had previously. A sink would be the opposite of that. That would be where the liquid is suddenly disappearing. So that would be something like where we had evaporation. Okay. And so those terms come to us from the context of fluid flow, but they apply for any vector field. If the divergence at a point is positive, we call it a source. If the divergence is negative, we call it a sink. Now, let's suppose I have a vector field, f of x, y, z, and it's f of x, y, z, g of x, y, z, 0. So I'm just going to suppose that the third component of my vector field is 0. So that way, if I had a point P naught, I could sort of draw a cross-section of that vector field, and I would know that that cross-section was the same in every plane parallel to the xy plane, because there's no z component here. So drawing things this way, the z component would be coming out from the board. I haven't drawn the traditional orientation for the three axes because the z-axis is irrelevant in this case. But basically there would be no component of my vector fields that would be coming out from the board or back in towards the board. So I can draw this two-dimensional cross-section of a point like so. And let's suppose that my vector field looks something like so. So essentially, I've got stuff is flowing pretty much consistently in this direction. But remember that the length of the vectors would correspond to, if this were a velocity field or a velocity field scaled by a density function, so that we were measuring not the volume of liquid flowing through, but the mass of the liquid flowing through, this corresponds to the speed with which it's flowing. So stuff is flowing faster in this direction and slower in this direction. So based on that, I can determine that P naught here would have to be a sink, because I have more stuff flowing into a small region around P naught than I have flowing away from that. Okay. So there are a couple of problems in the book that do give you a cross-section like this. The book doesn't do a very good job of specifying that they are working with a vector field that just has a 0z component. Okay, but that's essentially what's going on here. And you're basically just looking at a small region around P naught. Do I have more stuff flowing towards the point or more stuff flowing away from the point? And then I could classify it as a source or a sink. We could do something similar in 3 space. It's just hard to get an accurate picture that's of the 3-dimensional vector field. So we're simplifying things and just working for that sort of problem with a vector field that has a z component of 0.